Hello everyone, welcome to Unit 20 of online course on probability distributions. The last module we have discussed some numerical examples with respect to Poisson distribution. Now in this module also we are going to discuss some problems related with the Poisson distribution. And here we consider one recurrence relation, how to derive this recurrence relation for a Poisson random variable. This is the first problem we are discussing here. See, x is a Poisson random variable with a parameter lambda is given to you. And suppose we have the mu r dash, that is the rth arbitrary moment of the random variable x, then that mu r dash is obtained on the basis of the recurrence relationship mu r plus 1 dash is equal to lambda into mu r dash plus d mu r dash divided by d lambda, or derivative of mu r dash with respect to lambda. So, this is usually we call it as a recurrence relationship between arbitrary moments of the Poisson distribution. How to prove this? See, here you are given x is a Poisson random variable, x is a Poisson random variable. So, our f of x, that is probability mass function, you are given as e power minus lambda, lambda power x divided by x factorial, where x is equal to 0, 1, 2, etc. and lambda greater than 0. So, this is the Poisson probability mass function. And now we are deriving a recurrence relationship between arbitrary moments of the distribution. And arbitrary moments, let us consider rth arbitrary moment denoted by mu r dash. Mu r dash is, we know it is expectation of x power r. So, this is our rth arbitrary moment of a random variable x. So, for Poisson random variable, this is obtained as sigma over x, x power r into the probability mass function f of x, or that is equal to sigma over x is equal to 0 to infinity x power r e power minus lambda, lambda power x divided by x factorial. So, this is the rth arbitrary moment of the Poisson random variable. See, using the Poisson probability mass function f of x, we are finding the rth arbitrary moment of the random variable x, that is mu r dash, that is equal to this expression. So, just next what we are doing here, you have the value mu r dash, already we have written mu r dash, that is sigma over x is equal to 0 to infinity x power r e power minus lambda, lambda power x divided by x factorial, that is our mu r dash. We are differentiating this expression with respect to lambda, suppose. So, when we are differentiating that expression with respect to lambda, the left hand side derivative of mu r dash with respect to lambda is equal to derivative of the right hand side d by d lambda of sigma over x 0 to infinity x power r e power minus lambda, lambda power x divided by x factorial. Or that is same as derivative of sum of the functions is same as sum of the derivatives. So, you can write this is sigma x is equal to 0 to infinity d by d lambda of the function x power r e power minus lambda, lambda power x divided by x factorial. So, when we are differentiating the mu r dash with respect to lambda, this is the expression we have. So, after getting this expression derivative of mu r dash with respect to d lambda, we are finding the derivative of the expression the right side. So, let us consider derivative of mu r dash with respect to d lambda is equal to sigma over x is equal to 0 to infinity derivative of, see earlier we have the expression d by d lambda of x power r e power minus lambda, lambda power x divided by x factorial. That was the expression there. So, we are finding the derivative of that expression. So, x power r into x power r is not a function of lambda. So, x power r e power minus lambda you are differentiating, you have e power minus lambda into minus 1 and the remaining function that is lambda power x divided by x factorial plus second sigma over x is equal to 0 to infinity x power r, this is e power minus lambda into you are differentiating this function lambda power x divided by x factorial, that is x into lambda power x minus 1 divided by x factorial. So, that is the derivative of mu r dash with respect to lambda. Now, just look the first expression. This is equal to minus is taken outside sigma over x 0 to infinity x power r e power minus lambda, lambda power x divided by x factorial plus second expression, this is sigma over x 0 to infinity. Just look x power r and x, you have x power r plus 1 e power minus lambda and lambda power x minus 1, you make that as lambda power x itself. So, that means we have to divide one lambda here divided by x factorial. Okay. So, just look, this is nothing but sigma over x is equal to 0 to infinity minus expression is there x power r into this is our probability mass function of the Poisson random variable. So, fx. So, sigma x is equal to 0 to infinity x power r fx, that is the first expression plus 1 by lambda sigma over x is equal to 0 to infinity x power r plus 1. Again this also is our Poisson probability mass function. So, you write this as fx. So, we started from the derivative of mu r dash with respect to lambda and we obtain the expression like this, and that is equal to, see first expression, that is minus sigma over x is equal to 0 to infinity x power r fx is nothing but our mu r dash plus 1 by lambda, this is our mu r plus 1 dash. By definition of mu r dash, we know the mu r dash is expectation of x power r, that is our definition. So, using that concept, we have this is our mu r dash and this is our mu r plus 1 dash. So, we have derivative of mu r dash with respect to lambda is equal to this one, or we can write this d mu r dash with respect to lambda plus mu r dash is equal to 1 by lambda mu r plus 1 dash, or we can write mu r plus 1 dash is equal to lambda into the expression derivative of mu r dash with respect to lambda plus mu r dash. So, that is we derived mu r plus 1 dash is equal to lambda into mu derivative of mu r dash, this is mu r dash with respect to lambda plus mu r dash. So, the advantage of this formula is, if we know the first arbitrary moment, second arbitrary moment, third arbitrary moment, etc. values are obtained by finding the previous arbitrary moments, that is, you know, if it is mu 1 dash is available, you can find mu 2 dash. If mu 2 dash is available, you can find mu 3 dash. So, all the arbitrary moments are available from this recurrence relation. So, this is a very important formula with respect to arbitrary moments of the Poisson distribution. So, R is equal to, you can take R is any value from 0, 1, 2, etc. So, substituting the R values there successively, you will get the values of mu 1 dash, mu 2 dash, mu 3 dash, etc. Okay. So, next problem we are considering another problem with respect to Poisson random variable. This is actually a factorial moments. So, for a Poisson random variable with the parameter lambda, we can derive the factorial moments is equal to lambda power r. Very simple, and this is the factorial, using this factorial moments values, we have calculated the mean variance, the other center moments of the Poisson distribution previously. And what is the factorial moment of the Poisson random variable here? That is, suppose x is a Poisson random variable with the parameter lambda, our fx is equal to e power minus lambda, lambda power x divided by x factorial. Okay. And what we are doing here is we are finding expectation of x into x minus 1, x minus 2, etc. up to x minus r minus 1 or r plus 1, r minus 1. Okay. And that is sigma over x 0 to infinity x into x minus 1, x minus r minus 1 into e power minus lambda, lambda power x divided by x factorial. So, look, this is the expression of factorial moments x into x minus 1. Suppose we are finding rth factorial moment, x into x minus 1, x minus 2, etc. up to x minus r minus 1, that is equal to sigma x is equal to 0 to infinity x into x minus 1, etc. up to x minus r minus 1 e power minus lambda, lambda power x divided by x factorial. And next is how this expression is modified. That expression is modified. This is equal to sigma over x 0 to infinity. See, we have e power minus lambda, lambda power x divided by x factorial, and that x factorial common factors are cancelled from the, actually the expression earlier we have expression x into x minus 1 into x minus r minus 1 into e power minus lambda, lambda power x divided by x factorial was the last expression we have. See, this factor will be cancelled from here and the remaining factor is x minus r factorial. So, this is e power minus lambda is taken outside, sigma over x is equal to 0 to infinity, lambda power x minus r into lambda power r, this way we are writing, divided by x minus r factorial, and that is e power minus lambda, lambda power r, and this is a known result, we have sigma over x, lambda power x divided by x factorial, this is known as e power lambda, sigma over x. Okay. So, this is e power lambda. So, that is lambda power r. So, what we have the factorial moment, expectation of x into x minus 1 into x minus 2 etc. up to x minus r minus 1, that is rth factorial moment, is equal to lambda power r. So, that is why we have first is suppose you are finding x into x minus 1, this is lambda square. Suppose you are finding third x into x minus 1 into x minus 2, this is lambda cubed, etc. So, this is the rth factorial moment of the Poisson distribution. And another problem regarding the Poisson random variable, usually we have suppose we have two independent Poisson random variable, and we have already established that sum of these two independent Poisson random variables is a Poisson random variable. Sum of two independent or n independent Poisson random variables is a Poisson random variable. And basically or naturally a question arises here, is the difference follows Poisson distribution. That is, suppose you have a random variable x, that is a Poisson with a parameter say lambda 1, and y follows a Poisson with a parameter lambda 2, and we have already established that x plus y follows Poisson with a lambda 1 plus lambda 2. This is known as the additive property of the Poisson random variable. The question now here is the difference is a Poisson distribution, is x minus y is Poisson. So, the question is the difference x minus y follows Poisson distribution, and that is the difference will not be a Poisson distribution, it is not a Poisson random variable, and that can be established easily using the moment generative function. See, if x is a Poisson random variable with a parameter lambda 1, we know the moment generative function mxt that we established as e power lambda 1 e power t minus 1. That is our moment generative function. And similarly, y follows Poisson with lambda 2, we have the moment generative function of y is e power lambda 2 into e power t minus 1. Okay. So, the moment generative function mxt is equal to e power lambda 1 e power t minus 1, and myt is equal to e power lambda 2 e power t minus 1. And suppose we are finding the moment generative function of minus y, this is e power lambda 2 into e power minus t minus 1. Consider the moment generative function of the random variable x minus y, and that is mx minus y of t, and that is equal to mxt into my minus t or my, minus t. So, that is either you can write m minus y of t or my of minus t. So, substituting these values, so we have m x minus y t is obtained as m x t into m y of minus t, because x and y are independent, and substituted the values e power lambda 1 e power t minus 1 into e power lambda 2 e power minus t minus 1. And that is not in the form of an expression of e power lambda e power t minus 1. We cannot combine those two factors because it is e power t minus 1 and this is e power minus t minus 1. It is not possible to combine the two expressions and make it in the form of e power lambda e power t minus 1, which is the MGF of a moment generative function of a Poisson random variable. So, that is the moment generative function of x minus y is not similar to the moment generative function of a Poisson random variable. From that, from the uniqueness property of the moment generative function, we can establish that this x minus y is not a Poisson, random variable. So, very easy to establish that if you have the x and y are two independent Poisson random variables, sum of the Poisson random variable follows Poisson random variable or Poisson distribution, but the difference of the random variables need not be a Poisson distributed random variable, and this is established using the application of the moment generative function value of the Poisson random variable. And now, we consider some more problems related with the Poisson distribution. So, this is a problem of finding probability corresponding to a Poisson random variable. If we want to get the probability value of a Poisson random variable, the parameter value is, that is lambda is not. If lambda is not, then only we can find any quantities related with the Poisson distribution. And in this problem, lambda is not given directly. This is mentioned as the Poisson distribution have double mode at x is equal to 1 and x is equal to 2. From that concept, you have to identify what is the value of the parameter lambda. So, what we are doing here, suppose x is a Poisson random variable with the parameter lambda, and given that the distribution has mode at x is equal to 1 and x is equal to 2. So, two mode, double mode. This is a double mode situation, that is mode at 2 points for the distribution. And already we established that for a Poisson distribution, if x is the mode, we established that lambda minus 1 less than or equal to x less than or equal to lambda. We have established that for a Poisson random variable, if x is the mode, then that x satisfies lambda minus 1 less than or equal to x less than or equal to lambda. Again, note that x is a positive integer values. So, 0, 1, 2, 3 etc. values are possible for x. So, if lambda is an integer, say I, then I minus 1 and I are the values of the mode from this. So, if lambda is an integer, I minus 1 and I are the mode. So, a double mode occurred when lambda is an integer, and what is given to you, that is x is equal to 1 and x is equal to 2 are the modes, though that is this is 1 and this is 2. So, lambda value is equal to I is equal to 2 is given to you. So, actually you are given that the parameter value of lambda is 2 by giving the double mode at x is equal to 1 and x is equal to 2, we are getting the value of lambda as 2. Now, you can find the probability of x is equal to 3. So, what is probability of x is equal to 3? Probability of x is equal to 3, you should the probability mass function, you know, e power minus lambda, lambda power 3 divided by 3 factorial, and already we have the value lambda is equal to 2. So, probability of x is equal to 3 is equal to e power minus 2 and 2 power 3 divided by 3 factorial. So, that is you have the value, this is 8 divided by 6 e power minus 2. So, that means 4 by 3 e power minus 2 is the value of this, and you can calculate that value probability of x is equal to 3 as 4 divided by 3 e power minus 2 if the distribution has the mode at x is equal to 1 and x is equal to 2. Now, you consider another problem of related with the Poisson distribution. Here also similar to the earlier problem, here also the problem is actually finding the parameter value. You are given that x is a Poisson random variable and lambda is not given directly, and to get the value of lambda, an equation in terms of probability is given to you. So, what is given, that is if x is a Poisson random variable, suppose x is a Poisson random variable, x follows Poisson with lambda, and so the probability of x is equal to x e power minus lambda, lambda power x divided by x factorial. You just note what is probability of x is equal to. You have the probability of x is equal to is e power minus lambda, lambda power 2 divided by 2 factorial, or let it be 2 itself, 2 factorial is 2. And now, what is the next quantity we are given? That is in terms of probability of x is equal to 4. So, you find what is probability of x is equal to 4. Probability of x is equal to 4 means e power minus lambda, lambda power 4 divided by 4 factorial. And then again one more value we have, probability of x is equal to 6 you have to find, that is e power minus 6 lambda power 6 divided by 6 factorial. So, from the probability mass function we have this probability of x is equal to is obtained, probability of x is equal to 4 is obtained, and probability of x is equal to 6. Just to substitute these values in the equation, we have the equation is the equation, see our equation is probability of x is equal to 2 is equal to 9 into probability of x is equal to 4 plus 90 plus 90 into probability of x is equal to 6. So, this is given to you. Substituting e power minus lambda, lambda square divided by 2 factorial 2, 9 into e power minus lambda, lambda power 4 divided by 4 factorial plus 90 e power minus 6, sorry, e power minus lambda, lambda power 6 divided by 6 factorial. That equation is simplified. That equation is simplified. We have this e power minus lambda will be cancelled in all the terms. This is e power minus lambda removing. So, lambda square will be cancelled and this is 1. You suppose you have the value 1. This is equal to lambda square divided by, this is actually from this to, it is 3 by 4. So, it is 3 by 4 lambda square plus next one you simplified, it is 1 by 4 lambda power 4. So, after cancelling the common factors from both sides, we have, this is the equation, 1 is equal to 3 by 4 lambda square plus 1 by 4 lambda power 4, and that can be written in another form, lambda power 4 plus 3 lambda square minus 4 is equal to 0. Okay. So, 3 by 4 lambda square plus lambda power 4 divided by 4 minus 4 is equal to 0. From this expression, we are finding the lambda value. How it is obtained? That is, you can write this expression as lambda square plus 4 into lambda square minus 1 is equal to 0. Okay. Lambda power 4 plus 3 lambda square minus 4 is like this. And see, from here it is lambda square is equal to either minus 4 or lambda square is equal to 1. And this lambda is positive. So, we cannot take the lambda square is equal to minus 4 and lambda square is equal to 1 implies lambda is equal to minus 1, that is not also not admissible. So, the only value of lambda is here, lambda is equal to 1, that is the admissible value for lambda. So, that is, if the equation is given, that is 9 into probability of x is equal to 9 into probability of x is equal to 4 plus 90 into probability of x is equal to 6 is given, you have the value of lambda as 1. Now, just look what is mean. The question is about finding the mean and variance of the distribution. And for a Poisson random variable, we have, suppose x is a Poisson random variable with the parameter lambda, mean is equal to lambda, and that is we obtain as 1 and lambda. Variance is also lambda, lambda is equal to 1. So, that is, if we are giving the value of the, if we are having the value of the parameter, then we can calculate any quantity related with the distribution. It is mean is equal to 1, variance is equal to 1, etc. So, these are the problems related with the Poisson distribution. Again, another problem here, one more example we are considering. This is also something similar to the earlier one, that is, if x and y are independent Poisson random variables such that probability of x is equal to 0 is equal to probability of x is equal to 2 and the probability of y is equal to 1 is equal to probability of y is equal to 2, then find the variance of x minus y. So, this is another question related with two random variables, and those two random variables are independent Poisson random variables, but the parameter value is not given directly. So, first of all we have to find the parameter value of the x. If x is a Poisson random variable, you find the parameter value lambda, and y is also a Poisson random variable. So, you have to find the parameter value corresponding to y. Then after getting the parameters of x and y, values of the parameter x and y, then we are in a position to find the variance of x minus y or mean of x minus y or moment generated function of x minus y, etc. And how this is the simplified? See, you are given suppose x is a random variable with the parameter lambda 1 suppose. So, suppose x is a parameter Poisson random variable with the parameter lambda 1. So, we have probability of x is equal to 0 is probability of x is equal to 2 is given in the first equation. This is given to you. And that is actually simplifying, you will get this is e power minus lambda 1, okay. Our parameter we assumed as lambda 1 into lambda 1 power 0 divided by 0 factor, that is 1, equal to this is e power minus lambda 1 square divided by 2 factorial, that is 2. And that is simplified, you have lambda 1 square is equal to 2. E power minus lambda 1 cancelled. So, that is 1 is equal to lambda 1 square divided by 2, and that is lambda 1 square is equal to. That is lambda is 1, lambda 1 is equal to positive square root of 2. Lambda is always positive. So, we have lambda 1 is equal to root 2. And now, the question is how to find the parameter of the random variable y. So, you are given probability of y is equal to 1 is equal to y is equal to 2, probability of y is equal to 2. We assume y is a Poisson random variable with the parameter lambda 2. If y is a Poisson random variable with the parameter lambda 2, consider this equation. This is e power minus lambda 2 power 1 divided by 1 factorial, that is our probability of y is equal to 1. This is equal to e power minus lambda 2 power 2 divided by 2 factorial, or that is simplified, we have lambda 2, that implies lambda 2 is equal to lambda 2 square divided by 2, or that is again lambda 2 power 1, that is lambda 2 square, that is again lambda 2 is equal to 2. So, lambda 2 is equal to 2. Okay. Hence, y is a Poisson random variable with the parameter lambda 2, where lambda 2 is equal to 1. Earlier we got x is a Poisson random variable with the parameter lambda 1, where lambda 1 is equal to square root of 2. So, the question is find the variance of x minus y, variance of x minus y, where x and y are independent, you are given x and y are independent. So, this is actually variance of x plus variance of y. Using the property of the variance, variance of x minus y is nothing but variance of x plus variance of y if x and y are independent. And what is variance of x? Variance of x is the, for a random variable x having the Poisson distribution with the parameter lambda, variance of x we know it is the value of the parameter itself. This is a non result for us. So, variance of x is root 2, square root of root 2, plus variance of y. Variance of y is, lambda 2 is equal, this is 2, okay, lambda 2 is equal to 2. So, variance of x minus y is equal to 2 plus root 2. So, this is how we are finding a quantity related with the x minus y, variance of x minus y, or mean of x minus y, or moment generated function of x minus y, whatever it is. So, in all this type of problems, actually that the random variable follows Poisson distribution and our aim is to obtain the value of the parameter lambda, and after getting the value of the parameter lambda, then we are in a position to calculate any quantities or any probability values related with the Poisson distribution. So, these are some examples we have discussed in the Poisson distribution section. So, with this, let me wind up this session, and thank you for hearing this session. Thank you to all.